Well, hello everyone, and welcome back to Adrian's Digital Basement. In my recent past, I had a couple videos on the second channel about this IBM PC XT clone motherboard that I use in all sorts of videos when I test things, and this motherboard started having random memory issues where I could no longer get this thing to run reliably. And I spent 2 videos digging into all the potential issues with various logic chips and stuff on here, and I never came up with a solution. And then I have this AST Mega Plus 2 RAM card, and in a separate video, I was trying to get this thing working, and this was also having random RAM issues. Now, I never connected those 2 things together. In fact, the testing of this card wasn't even with this motherboard. I used a different motherboard, but I think I might have figured out what was actually wrong with both of these. Now, because I was having so many issues and I was unable to fix both the motherboard and the RAM card, I asked my friend David, who was the same person who wrote the March RAM testing for the Apple II and the TRS-80 Model 1.3 and the Model 2, and I asked if he could port that stuff to the IBM PC XT. It was my thinking at the time with a better RAM test that maybe I could actually get to the bottom of what was wrong with both of these parts. Well, in the end, I didn't end up needing the RAM test, but the RAM test was still written, and it's actually running on the computer sitting here behind me, and I think it's a pretty cool diagnostics for these old types of machines. Think MemTest 86, but designed for XTs. So I'm going to talk about both what was wrong with both of these things and this cool new RAM test that we've come up with. So without further ado, let's get right to it. First, let's go over the problematic motherboard here. So this is a PC XT clone. It's 4.77 megahertz, nothing special, 640K, ISA slots, 8088. I mean, it's all pretty run-of-the-mill, and these things, they're pretty common, especially back in the day. Low-cost computers often used stuff like this. Now, this motherboard was always my go-to motherboard for testing, and originally I got this thing, I don't actually remember where I got it, but I've had this thing for a number of years, and this thing actually had suffered some battery damage. And after cleaning up the battery damage, which if I recall was in one of these slots here and around these ICs here, the motherboard worked, except if you tried to access the floppy drive, it would freeze up. Well, it turned out that there was a problem with this IC right here where the battery had leaked onto it and probably damaged it, and this has to do with the DMA. And on the IBM PC, whenever you access a floppy drive, it's actually using one of the DMA channels. And it turns out that that IC handles a bunch of DMA stuff, and because the battery, which was probably from a multi-IO card that was plugged into this computer at some point, had leaked on that chip and damaged it, that DMA channel for the floppy drive controller just wasn't working properly. So the machine would lock up anytime you tried to boot the machine or do anything with the floppy drive. So I removed the old IC, installed this 74LS373, which I think is a latch, and then the DMA channels were working and the floppy drive interface was now working perfectly. I think at least a year had gone by since I did that repair to get the floppy drive controller working, and I used the motherboard plenty of times on camera for testing of various peripherals and things like that. And then came the Book8088. This was sent in by a viewer, and this machine was not working. It wouldn't even post. Well, there was a video on the main channel about repairing this, which I'll link down below as well, and it turned out that I needed to replace the bus controller IC, which is just a standard PC architecture chip. It's the 8288, and it had become flaky in this machine. If I pushed on it, I think I showed this in the video, but if I pushed on the chip in certain spots under this cover right here, the computer would actually start to boot. If I let go, it would stop booting. That bus controller IC is totally imperative to the operation of all PC XT and the original PC 5150 as well. So if it's not working, well, your computer is not going to work. Well, I didn't happen to have one of those chips in stock to fix this machine, so I actually went to this motherboard and I just stole the chip right off of it, and it's right here, the 8288. I removed it, stuck it inside the Book8088, and then the book was working. This thing, on the other hand, no longer works. I took that chip out of there, so that's where the memory problems with this motherboard began. I replaced the 8288 with one I did have in stock. I found it on an old junk card that I had I stole other parts off of, and when I put it on this motherboard, it actually started exhibiting all these RAM problems. Now, I thought it was the 8288, but I'd actually ordered several more of them off eBay, and those came, and putting those on here made this thing not work. And that brings me to this motherboard, which is the twin XT clone. They're very, very similar. They're not identical, but they're nearly identical. In fact, the main difference, though, or the way I can tell these apart, is this has 2 power connectors here, And the one that I started with having all the RAM issues only has one installed in the board, has the holes there for the other one. In addition, the second twin motherboard has every single IC on it in a socket, so that's pretty handy, while this one has almost everything soldered except for the CPU and the ROMs and the RAM, stuff like that. The 8288 that was not working or didn't seem to be working on this motherboard worked in this motherboard. So clearly it wasn't that. So in those 2 second channel videos, I spent a whole bunch of time troubleshooting all sorts of things on here, and I think I ended up socketing some more ICs after doing a whole bunch of diagnostics and going through the schematics of the original IBM PC XT, which this is a clone of for the most part. It's a little different, of course. And I never got to the bottom of what was causing all the random crashes. So with 2 videos that were over an hour long each, I was just left with the disappointment that this thing was still not working and I had no idea what was going on. In fact, at the end of that video, I took all the RAM off the problematic motherboard and I put it on the one that, well, is working properly, never had any issues, the twin here. And it really, well, it changed a little bit actually. Putting the RAM from the good motherboard, the twin good motherboard, onto here resulted in it kind of working better. I had like 256K on here and I could actually boot DOS and it was kind of working. So I don't know, it was really strange. And then as far as the AST Mega Plus, this was a main channel video and I got this in a box of random stuff and I went to test it and I thought, okay, this is going to be easy, it's just going to work. And after some figuring out that it did have a couple bad RAM chips that were actually bad, and then I figured out through some trial and error how the dip switches work, because you need to configure those for these types of RAM cards to work. They need to coexist with the RAM that's on the motherboard that you're plugging it into. This thing was acting up as well. We were just having all sorts of random memory issues. And in my troubleshooting, I ended up socketing this buffer here, the 74LS245, because I thought maybe this has something to do with the random RAM errors. Because what was happening on the card is if I was using the DOS debug program, I would read some of the memory out of this thing and it would look a certain way and I'd read it again and it would look different. Like it would have these weird error patterns in them that just didn't really make sense, because when I swapped out this buffer IC, what would happen is those patterns I would see would change. And sometimes it would read correctly and other times it wouldn't, and it was all very random and made it where you couldn't use this card. If you put this into your computer, it would absolutely just start crashing. And I actually did all my testing of this AST card in this motherboard. This is the twin motherboard that's never had any issues. But with this card in there, the RAM on the motherboard, which was 256K at the time, it was just this first bank, it would work without issue. But anytime you went to go to access the RAM here, it would completely not work, it would crash, parity errors, you know, the whole 9 yards. It just was not functional. So all those RAM problems is what led me to ask my friend David, who lives locally here in the Portland area, to write that March test ROM for me. He had already figured out how to implement a March test on the 6502 and on the Z80 processor, so we figured that porting that over to the 8086, 8088 architecture wouldn't be that difficult. The one added complexity to writing a diagnostic ROM for a PC versus for the Apple II or the TRS-80s, for instance, is that when you turn on an Apple II or a TRS-80, it's just fully initialized. Everything is just ready to go. The processor doesn't really have to do anything. If you don't have the processor installed in those computers, or a ROM, for instance, the video comes up and you have a bunch of garbage, you know, it's displaying what's in RAM, which is where the characters are stored, onto the screen. All that stuff is just kind of ready to go. There's very little setup you actually have to do. That is very different on the PC architecture. This is much more complex than those systems. Not to mention there's no onboard video on the PC, so you have to support displaying video on CGA adapters or monochrome adapters, and that involves initialization. Those cards have 6845 CRT controllers that require setup and parameter tables, and you know, all sorts of stuff has to happen there. Not to mention the ICs on the motherboard also need some setup to get the system running. You have to set up the DRAM refresh, which is through the DMA controller. There's things like that that you have to do. Well, luckily, there is source code out there for ROM BIOSes, including IBM's original stuff is out there, but even the PC Turbo open source BIOS that I was using on the motherboard, you can just look at that code to see how it's setting up the system, and that is a great base to start from so that you can actually get the system initialized and figure out what the bare minimum is to get the system running, and then go from there and start doing the RAM testing. Now, the diagnostic ROM, which is in very early stages of development, but it is functional, and I think it's pretty useful if you're trying to troubleshoot some RAM problems on some of these old systems. It's open source. It's going to be available on GitHub. Of course, I'll have a link down below. By the time the video comes out, I will definitely have the code up on GitHub so you can take a look at the diagnostic code itself, and you can download the binary files to run it on your system if you want to try it out. But for now, I don't have a GitHub repo to show, so we're just going to show off the diagnostic ROM itself, and I'll talk about it a little bit. So what I'm going to do is I'm going to use the twin motherboard here, which this thing never had any issues. This thing uses 8K EPROMs. This is the actual startup code for the system. It's 8K, and this is where the CPU jumps to when you power on the system to actually begin executing code. So you don't actually need to have these chips in there for this diagnostic ROM to work. It simply needs an 8K ROM. This is a 2864. It's one I got from AliExpress, which is why it doesn't really have good markings on it, but it's an Atmel chip. But any 2764 EEPROM or 2864 EEPROM will work fine in these types of motherboards, these clone motherboards. If you're going to be using a PCXT, there are two BIOS chips on that, and they are both 32K. They're 27C256s. This 8K ROM will still work fine on XTs. You just have to burn a 32K EEPROM with the 8K image at the very top. And we'll just have a 32K file for you to download so you can put that into 27C256 to get it tested and working on your XT. Now for the IBM PC 5150, that's the very first PC IBM released, they use mask ROMs that have the pinout of the 2364 on them. They cannot accept 2764s or 2864s like these without an adapter. And you can buy them very inexpensively online, the little PCB adapters. So I just recommend getting one of those adapters or building one yourself. You could take two sockets and stack them on top of each other and just use a few bodge wires to rewire it. For demonstration purposes, I'm going to use this IBM official CGA card. This was the one I made a couple videos on where it had a ton of battery damage in this area and it was actually thrown in the trash. So I took it out of the trash, cleaned it up, and got this thing working and did some mods to it to see if I could make it work faster and stuff like that. The diagnostic ROM, which I have flashed into the 2864 here, only supports CGA and monochrome right now. You cannot use EGA or VGA. So unfortunately, if that's all you have, you're gonna have to procure yourself a CGA card, for instance. There's no need to plug a keyboard in or anything else because the diagnostic ROM does not use or even initialize any of that stuff. Okay, so here we go. Let's turn this on and it should initialize right away, and there it goes. It is now testing the memory. Now let me talk about why I think that this is one of the best RAM tests out there for the PC, that's ROM based at least. Well, let's talk about this. Some of my requirements were that this could run with no memory installed in the motherboard at all, and it can. If you take out every single RAM chip and you put this diagnostic ROM in here, you will still get the system to start up. You will still see this exact screen. And what it's doing right now is it's running through a bit pattern test. And of course, if we have no RAM installed, all the RAM will be bad. So, you know, it's not going to be particularly helpful. Yeah, you have no RAM in there, but the diagnostic test will just keep humming along and running, looping over and over again and doing all of its testing. Now, what happens with a lot of processors, including the 8088 that's on here and the 8086 and all the Intel processors and pretty much everything else, is you need some amount of memory somewhere to put the stack pointer. The stack is so important on these early processors because they didn't have that many registers on them. And the registers are there, think of them as like very high-speed little tiny pieces of memory that are inside the CPU. Well, 6502 especially has so few of those, but even the 8088 doesn't have that many, that you run out of those registers very quickly. And typically when you have a stack, you can imagine it's like a stack of papers. You would take a value out of the register that you need, it's important, but you just need more space in your registers. You need to put it somewhere temporarily. You stick it on the stack, think of a stack of paper again, and that is stored in memory somewhere. And then when you need that information back, you can grab it off the stack and put it back into the register and then continue running whatever routine you're doing that needed that information. Now, with a somewhat complex RAM test, you need to have subroutines that run different parts of code. You need to jump around inside the ROM space, and that all requires use of the stack. On any 6502-based machine, the stack is at a fixed location in memory. So if the memory is bad or not there in that spot, then the processor has no access to the stack. You have to carefully write the code that does the RAM testing to not need to ever use any of the stack instructions. And that means you have no access to subroutines or things like that. You have to kind of unravel the entire code, which makes it very big and inefficient, but it is possible. And that's how the Apple II dead test ROM is working. And if we ported it over to run on the Commodore, or you actually look at the Commodore dead test ROM that they released, the initial phase of that diagnostic ROM also runs in a way that doesn't use any memory whatsoever. Now, a big difference, as I alluded to earlier about the Apple II or the Commodore and something like this PC, is that the display output on the Apple II and on the Commodore requires the main memory to be there. If you don't have working memory, you cannot display any text on screen. So with the Apple II, we're relying on on beep code to try to tell you that, hey, there's a problem with a specific chip. You might want to go change that. And once it gets past the initial phases and it goes, okay, there's enough memory working that I can display text on screen, well, then it does that and then it tests the rest of the memory. On a PC, on the other hand, well, the video card, like the CGA card that's installed here, has its own RAM on it. So if your video card is working, the ROM can initialize the video card and display some text on screen. But there's something else you can do as well. On the 8088 processor, the location of the stack is not fixed. It can actually be moved to any location in memory. Well, it turns out the CGA card and the monochrome card has memory mapped RAM. So part of the RAM, which I'm pointing to it right here on the CGA card, it ends up in the memory map of the processor. So all you need to do is tell the processor, hey, your stack is here. It's over inside the video card. So what the diagnostic ROM does is on power up, it actually does a test of the RAM on the card, does a March test. So it's a comprehensive RAM test as well on the card. And if it's working, it initializes the video, sets the stack pointer to there, and then it starts running the main code for testing the motherboard RAM. And that is how it can run completely without any motherboard RAM installed, period. Now this is very different to the way the IBM BIOS runs, the one that's on the motherboard stock, or even these third-party ones. They rely on the first 16K of memory on your motherboard to be working properly so they can set up a stack and even do any further post instructions. A lot of times with these ROMs, if the first 16K of RAM on your motherboard is not there or it's not working, it won't even initialize to the point where it makes a beep code. The motherboard can seem entirely dead. But the reality is it's not dead, there's just a RAM problem in there. And that's where diagnostic ROMs that don't rely on the motherboard RAM for the stack pointer can come in handy. And our new diagnostic ROM here, just like Judd's Diagnostic and the SuperSoft ROM, which is in here, does not rely on the main motherboard RAM at all for that initial setup. So it's able to initialize the video and let you know that your computer is actually working and it's not actually dead like it seemed like it was with the original BIOS. If these other diagnostic ROMs can do this, they can start the system up without any RAM in the motherboard, then why do we even need another diagnostic ROM? Well, the reason why is I have found through a bunch of testing that the RAM test that's in both the SuperSoft one, well, especially this one, but even Judd's Diagnostic, which is modern and came out in 2024 and has source code available, is not testing the RAM in a comprehensive way that will find all the potential errors. And this is where this ROM and this RAM test comes into play. David implemented a March U testing algorithm, which is somewhat modern by RAM test standards. It's not really that modern. It just seems like, well, back in the day, no one was using anything comprehensive enough. And there are actually types of RAM problems that you can encounter on these motherboards that will create a system that crashes, but that Judd's Diagnostic ROM and the SuperSoft ROM, and then of course the stock BIOS ROMs, like the PC Turbo one and even the IBM one, will not detect. And you'll only know there's a problem because you try to run your computer and it crashes and you get parity errors and stuff like that. You just have no idea what's wrong. The problem with parity errors that when they pop up is they just show you the address that's bad. They don't tell you what chip is bad. And in a system like this, there are actually 8 chips that are making up each bank. So with an address, you can, with enough figuring out, you can figure out which bank it's in. But if the RAM is soldered onto your motherboard, I mean, you're gonna have to desolder every single chip until you figure out which is the bad chip. I want a diagnostic ROM that was available to people that would not only have the state-of-the-art modern testing algorithm, which is March U, but then tell you specifically which bit is bad, which will directly lead you to what chip is bad with just a little bit of math. Not that hard to do. And then the final thing that I was really asking for with this test is I wanted something to run indefinitely. So even if errors were encountered, I wanted to just show the error on screen and then just keep looping forever. That would allow you to run a burn-in test on your system and then go away, run overnight, and then come back the next day and feel confident that the system was fully operational, the RAM was solid. While there are RAM tests that you can run in software for the PCXT, like Check It as an example, and that will run indefinitely. That exists, but the problem is if you can't boot into DOS because you're having other RAM issues, it's too unstable, then you can't actually run Check It, so that's no help. And then a bunch of the other tests either have display issues where they don't show you all the errors in a grid like this, they might show you the last error, or they just halt entirely when an error is encountered. So that's really not much of a burn-in test. Unless the system is working perfectly and just will run indefinitely, then okay, you can feel confident if you come back the next morning and you have 50 passes there. But if there's any kind of RAM error that does happen, it just halts. And sometimes it's really good to let it run overnight because it might take a long time to identify these errors. And I feel that this test will do that. So I know at this point I'm talking just about the diagnostic ROM, and I want to do some demonstrations of causing some RAM errors on this system by putting in some bad RAM chips, for instance, and showing you what the RAM errors look like and talking a little bit more about the algorithm. Now, when it comes to the motherboard here that wasn't working and I said is working now, I'll get to why it's working and why this is working in a little bit. But I just want to talk about this diagnostic ROM because I think it's really darn cool. All right, so I'm going to power the computer off and power it back on. Let's talk about what happens here. So first thing that happens is it does that RAM test on the video card. You don't see it happening because the video is not initialized yet. So then it initializes the video and, well, it starts running the regular RAM test. Now the snow you see running here is a side effect of the CGA card. It's nothing to worry about. That is because this CGA card displays snow when its memory is accessed directly, which is exactly what the ROM is doing. But you can run this on MDA or you can run it on another CGA card that doesn't show snow and you don't have to worry about it. So the first thing this thing does is it runs through some bit pattern tests. And you can see it says pass 1 at the top there, bit pattern 55. This type of testing is pretty much how all RAM testing works on the original PC. The original IBM PC BIOS had a little bit more sophisticated RAM tests going on than just simple bit patterns, but barely more capable. But then the PC Turbo BIOS ROM, and in fact, I looked at a couple different ROMs, they all work with simple bit pattern tests, which is, it can detect some issues, but it's very, very rudimentary. Now we have various different failures you can have with RAM chips, and I've sort of run into everything at this point. You can have a problem where the RAM chip is just stuck on or off all the time, where no matter what you write into it, you always just get zeros or get ones back, right? So that chip is just totally dead. That type of failure will be caught pretty easily by just a standard bit test. So what's in the BIOS ROM when you turn the computer on, it should be able to find that, no issue. Now, as long as the reporting that the BIOS has is actually usable, like it tells you, hey, the problem I'm seeing is at this address or these addresses, and it's in this specific bit. As I mentioned, this motherboard has 1 bit wide memory. Each chip here is only 1 bit wide. So if it just tells you the memory address, that doesn't really help us because we have 9 chips here. It's really 8 plus parity, and any one of those could be bad. And it's not likely they're all bad. It's just one of them is going to be bad. So I found that the reporting of which bit is bad is very lacking most of the time. I think the IBM BIOS, though, actually is the one that does have decent reporting, but it seems like all the third-party ones pretty much don't. Another type of problem you can have is just random cells inside the memory chip are bad, or even just one cell is bad. So everything else is working perfectly except for one memory location. That type of problem can usually be caught with a bit test as well. So you won't really have a problem figuring that out. The same kind of things apply as I just talked about with the fully dead chip. But then we have some of the more difficult to detect failures in the RAM chips. One of them is that the circuitry inside the RAM chip has gone bad, and when you write a value to one location, it might write to that location, but it might also write to somewhere else in the chip, or it might affect the cells that are next to it as well. And it might only do that sometimes, or with certain values that are written into the chip, or certain patterns exist in there that you might start to see those types of issues. Well, those types of problems are really hard to detect, and there's a reason why. Unlike the Commodore 64 or the Apple II, the size of the memory chips that are in use on a PC are not standard. You can have 16 kilobit chips, you can have 64 kilobit chips, you can have 256 kilobit chips. Theoretically, you can have 1 megabit chips where you might have full 640K with just 8 chips. That would be kind of rare on an XT, but it is possible. But worse yet is you often combine RAM on a card like this with what's on a motherboard. So you might have 256K on the motherboard just in one row of chips, and then the rest of your RAM exists on a card like this using 64 kilobit chips. Because the diagnostic routines that run these RAM checks don't know the size of the chips, I mean, it's not really relevant, so it doesn't need to know it, but it does make detecting those types of weird issues more difficult. And really that is because most of these RAM tests that exist inside the BIOSes only test RAM in these little chunks. And I think it's usually like 4K or maybe 16K. They sort of do it in the minimum size of the RAM that was supported on the system. And therefore, if you write to one location in a chip that's say 256 kilobit, and it affects something that's like far away in the chip, well, the RAM test is not expecting that. And it just checks the 16K, it says, oh, that looks good, moves on to the next 16K, so on and so forth, and it will miss those types of errors. Another type of problem, which is kind of similar but different, is a page error. And if you can imagine a 64 kilobit chip, like on the Commodore 64 or on the PC here, those chips are the equivalent of 4 16K chips, that are all inside of there. Well, what can happen is the address lines, the row and column address lines that go into the chip, if one of those is bad, like for instance, the socket is damaged, the pin is bad, or even inside the chip, there's a failure of some kind, what looks like a 64 kilobit chip can only be addressed as, say, a 16 kilobit chip, or a 2K chip, or a 4K chip. It just depends on which address line or lines has gone bad. Well, here's a problem. Imagine a 256K chip is running as a 64K chip, or even you take your motherboard and say you're installing the RAM chips in here and you accidentally put a 64K chip in one of the locations that should have been a 256K chip. It's just going to mirror that chip over and over and over again 4 times. So if you fill it up with a pattern of zeros or Fs or whatever, it's not going to look bad. And that's because when it goes to write all ones or all zeros into the chip, or even 010101 or whatever pattern, well, it's just going to be repeating that pattern over and over and over again, and it's looking for all ones, and it's going to see all ones. So those page errors are really insidious, and almost never have I found any of these diagnostic routines ever be able to detect those, but I've definitely had that particular failure mode happen on RAM chips before. Now, the IBM PC, the XT, and the clones pretty much all have parity memory checking, and that's an extra RAM chip in there to just help it detect potential issues with the RAM. And it works pretty well. It would detect a page error like that. If one chip was installed on the motherboard with a page error and you tried to write program code into there, like boot into DOS or whatever, the computer would very quickly crash because the parity RAM chip that's installed there, well, that chip has all of the bits available to it. So that parity calculation is going to say, hey, you wrote this stuff into that chip over there, and you know it didn't work because it's actually a 64K chip and a 256K socket. Well, the parity error will be thrown, and what you'll get is a particular address of a bad memory location, but it won't tell you what bit is wrong. That's back to what I was talking about before. It'll just say, oh, there's a parity error, it's at this location, boom, and the system just halts. At best, if you have a parity error or a RAM error that's generated with just a simple address and no other information, all that's going to tell you is which bank it's going to be in. And that's only if you're able to figure out the bank layout of your motherboard. I happen to know on the original XT and the PC and even these clones, bank 0, 1, 2, 3. And the address space, of course, this is 256K, these two banks, but that's probably not always like that, but on this motherboard it is. And these two are 64K each. So you have to do a little bit of calculation to figure out where in the memory map this might exist, and then at least you're going to know, well, which row of 9 chips the error's in. But without the bit, you still don't really know which one it is. Of course, that adds a whole extra complexity when you add a card like this, because we don't really know how these are laid out. There's no standard there. The clone motherboard's pretty much copied the PC, but these, on the other hand, unless you can find the schematics, you're gonna have to do quite a bit of toning out to figure out how this stuff is laid out. So back to the diagnostic ROM. It runs through all the bit tests and it runs various passes here. Now it's writing AA to every memory location, and you can see after a bit pattern tells you what it's writing. And if any errors did come up, it would show up in these little dashes. And I'll demonstrate with some bad RAM chips. I went and gathered up some bad RAM chips here, so we'll try those out in a second. Now this particular ROM, even though you see little boundary marks there, like 64K, 128K, you'd make it think that it was actually testing the RAM in little chunks. It's not. So you see it says March U1. It started with 0, or it just initialized all the memory again, and now it's writing information into all the memory locations of the entire system. Whether the memory is there or not, it's trying to write to all 640K. It does not test the upper memory. Now it says March U2. Now, you might think this is just like a second pass of the March test. It's not. It's just part of the main March U test. And with the March test, it's a bit too complex for me to explain it here easily, but the gist of it is, what it does is it goes through memory after it fills it all up, and then it inverts it. So it reads like the bit that's there, and it writes back the opposite bit. And it goes through and does this multiple times. Now you can imagine if things are working properly, like you can imagine this needle nose here. If I flip it over and then I flip it back and I flip it over and I flip it back, well, I'm gonna end up in the same orientation that I started with the little bent part facing up. But if there's a problem in the memory that's subtle, where reading or writing to another cell somewhere else in memory can change the value, the orientation of my pliers here. Like if I flip this screwdriver over and it somehow flips this, it shouldn't, but it somehow does. Then when I go back and I flip this over, back, well, if writing to this flipped this over, then when I've gone and just blindly inverted this a few times, what I'm done, instead of it facing up like it should and like all the other cells do, it's now facing down. And that tells us right there that there's some issue with this cell being affected by another cell, or it's just bad, or whatever, any kind of issues like that. The March test is super good at figuring that out. And because we're treating the entire 640K as one big chunk, we don't just test little pieces at a time. No matter what size your RAM chips are, like if you have 1 meg RAM chips, it doesn't matter. This is going to detect if a cell up in near the 640K barrier is written to and it flips something down around 2K, it's still going to be detected by this particular March test algorithm. So what the March test does, you can see it's going backwards now, is it goes both directions. So it writes all the memory, then it flips it, flips it, flips it, flips it, flips it, flips it back, and then it goes backwards, starts from the other direction and flips it, flips it, flips it, and does that twice. And that going both directions is required for figuring out exactly where the page errors are happening. This is useful because page errors where the memory is mirrored multiple times may not be detected if all you're doing is going up, because you're seeing that 64K multiple times and you're like, oh, everything is fine. But when you go backwards and you go down, what you've written up here is actually affecting that first chunk there, and all the mirrors actually. And as soon as you go to read and write one of the other mirrors, you're gonna go, oh, this has been disturbed and the bits have been inverted when they shouldn't have been. I shouldn't have actually changed these. And that is a clue right there that there's a problem. I will put a link in the description below to more information about March testing and why it's so valuable. And it's really the only good way to do RAM testing. But just trust me when I say that it's a really good way to test RAM. And if you're not doing a March test, your RAM test is pretty much incomplete. And while it's going to catch some errors, it's probably not going to catch all errors. So why don't we cause some memory issues on this particular motherboard so I can demonstrate how things look. These two rows of chips here are 256 kilobytes. I'm just going to take one of them out. And first what I'm going to do is I'm going to insert a 64 kilobit RAM chip, but it has a dot on there because this is a bad chip. I already know that this chip is not good and doesn't work properly. And when the bit pattern test reaches this chip, it should automatically flag it as bad. And there it is. It is now showing 04 for that entire bank. Now I put it in the second row of chips here. This row of chips is 256K all the way to 512K. So the bit pattern test detected this RAM chip is bad right away. Now we have a double whammy here, right? Because this is not only a bad RAM chip, but it's also a 64 kilobit RAM chip when it should be a 256 kilobits. And well, because the chip is bad, the bit pattern test is detecting it. Now it's showing us 04. Now how do we go from that to figuring out exactly what chip is bad on the motherboard? All we need to do is use a hex to binary calculator. Since this diagnostic ROM is designed for XT systems, it's only designed to test 8-bit wide memory. Now on this motherboard, we only have 8 possible bad RAM chips, and it's data bit 0, 1, 2, 3, 4, 5, 6, and then on the back side of the card there, 7 and 8, and there is a parity RAM chip, but this test actually does not test the parity RAM chip whatsoever. It completely ignores those. Well, one of the other requirements for the diagnostic ROM is you need to be able to report that there's one chip that's bad or multiple chips that's bad, up to potentially all 8 of the chips. So the easiest way to report that, when you're talking about a grid, we have to report potentially a whole bunch of bad memory. The easiest way to do that is to represent it in hexadecimal. FF in hexadecimal is 256 in decimal, or all 8 bits are set to 1. In our results, if there's a 1 reported in any particular location, that is the data bit that is bad. And if you look at the output here, we can see that we have a value of 04 reported. Well, to figure out what bit that translates to, all we have to do is go to a calculator like the Windows calculator, turn it into programmer mode, go to hexadecimal, type in 04, and then we can look at the binary representation of 04. Well, if you think about this right here as being data bit 0, and data bit 1, data bit 2, and there's a 1 in that location, it's telling us that there is a problem very specifically with the chip in that memory location, or locations, plural, in data bit 2. And this is where it takes some knowledge of the system that you're working with to know how the bits are mapped. Now, I happen to know that on this motherboard, this is bit 0, so all of these chips here in the 4 banks is data bit 0, 1, and 2. And we know from the results that there's a problem in the memory from 256K all the way to 512K in data bit 2, and that happens to be this chip right here. Now what I'll do just to demonstrate is I'll take out another chip here. So now there's a chip missing and then there's a bad chip. And we turn on the system, and once we get up to that second bank, it's now going to have a different value there. It now has a value of 14. And if we go to hexadecimal, we type in 14. We now know we have 0, 1, 2, 3, 4. And on PCXTs and the clones, 0, 1, 2, 3, 4. So right away, it identified these two chips are bad. All right, I'm gonna take this bad chip out of here. I'm just gonna stick it randomly into one of these lower locations here, the 64 kilobit stuff. And I'm gonna take a perfectly good 64 kilobit chip that does not have any issues, and I'm gonna stick it into this memory location here in bit 2, where we used to have the bad chip. Remember, the wrong chip is in here in that upper 256K, so 256K to 512. And notice the bit pattern test is not detecting any kind of problem. Now down here we should. Okay, so it's in the last bank of memory, which is just the last 64K, and it says 08, and we happen to know that that means bit 3 if you use the calculator there. And of course that chip is in bit 3, so that was very helpful. But I wanted to demonstrate that the bit test is not finding this 64K chip that is in this 256K bank. But I can guarantee you if we put a regular BIOS into this thing and boot it, it's gonna pass the memory test. Well, not with this bad chip in here, but if I take that out and put a good 64K in, it will pass its memory test, but DOS will very promptly crash. All right, here comes the March test, and it will be able to find that this 64K chip is installed in here. And it's interesting how it works. It goes back to what I was talking about before, how the March test goes forwards and then it goes backwards. It is now testing the part of memory that should be causing a problem, right? And we didn't see anything yet. Well, it's testing there in the upper part, but that's fine. But here it is going to start catching that there's a problem because it's doing those inversion stages, and oh, right away it's telling us that there's a problem with bit 4. But it's not in the entire upper 256K. It's only in the third, the 3 mirrors above. Well, that's because that first 64K in that 256 is working properly. But what's going to happen is it's now going backwards, and it's going to be able to see that that first part has been affected by bit flipping in the upper areas. It's not done yet, so notice it kind of went past there, and you might be thinking, oh, it didn't detect that first part is wrong. But it will in a moment, and that's because it's in the middle of doing those inversion stages. And it's funny, all the snow happens there because as it's detecting bit errors, it's accessing the stack a lot. Remember, the stack is on the video card. And there it goes. It is now detecting all the errors that exist there. And because that first 64K is actually good, there's not a problem with that first 64K in that upper 256 where there's a problem, but it's being mirrored. So any writes to that upper part of it affect it in a negative way, right? So that's why it's saying it's bad. And we happen to know from our calculation we did earlier that hexadecimal 4, which is representing as the problem, happens to be bit 2, and it's in bank 2, and that's right here, 0, 1, 2, and that's the chip that is the problem. Okay, so I just took out the bad 64K RAM chip and I put the original one back in. So the only problem on here right now is we're getting a page error on this one particular RAM chip. Let me remove this diagnostic ROM and we'll go back to this random clone XT BIOS here. I think this BIOS was actually found on the twin motherboard, the one that never had a problem. It's just one of many. I can ignore that, that's normal. It's one of many. This is the one that says system already, as opposed to system ready, system already, whatever. This thing obviously has the most garbage RAM test imaginable. It is a bit pattern test. It does detect if I put one of these bad RAM chips in, but notice, it did not find a problem there. And there absolutely is a problem. The problem being that I have a 64K RAM chip inside a 256K bank. There is a page error right now. So let's pop in the XT IDE so we can actually boot this system, and of course a keyboard. And as you can see, the XT IDE BIOS is running, and this thing is gonna try to boot DOS, and it's very quickly gonna crash, and it will result in a parity error. It should result in a parity error, let's see. It's possible this BIOS has parity error disabled. Well, so far nothing's crashing, but let's run check it. You can ignore the snow, that's just my modified CGA card. Check it might just crash. There we go, parity error. So I think it will give us an address, and there it is, it says continue. So it's telling us there's a parity error at hex address 4000. Now I happen to know on the motherboard here, 0 to 3 FFFF is the first bank, 4000 to 7 FFFF is the second bank, and you can figure that out if you just look at a memory map and you look at the addresses. So at least it's telling us there's a problem in the second bank. That is actually helpful, but as I mentioned earlier, you can have motherboards where every chip is just soldered down, and if it doesn't tell you which chip is bad, well, how are you supposed to know which chip you need to desolder and replace? That's where the diagnostic comes in. Okay, I'm just gonna take out the system already BIOS and we're gonna put in the PC Turbo one, which is the open source and much more modern BIOS. In fact, like this is the one that is running on the Book8088. And I haven't tested this, but I'm quite sure that its RAM test is not going to be able to detect this page error, and we will get a very similar crash with DOS, or at least running check it. If we try to run any program that loads anything into that chunk of memory, system is going to crash. There we go. It just worked. No issues. Now, I happen to know DOS 622, which is what I'm using here, mainly loads itself a little bit into the lowest part of memory and then also into the top part of memory up around the 640K range. So therefore that middle chunk is unused until you load a program or game or whatever. So we'll run check it here and it's going to crash in the same way. I'm assuming, yep, there we go. Looks exactly the same. It's funny how it looks identical. Oh, it says continue. It's telling us the same thing, but we can see that there's an issue. So you might be thinking, oh, okay, well, let's take this out and we'll pop in the diagnostic ROM, that landmark or super soft one that's floating around on -0 degrees. So we get that in there, we turn it on. Well, I have tested this, and unfortunately, the RAM test in here is no good either, and it is unable to detect page errors whatsoever. And you can see it's so far detected no problems and says all the memory passed, all 640K, working perfectly. We know that's a lie. The system will crash if we try to use it. And I can tell you, we can let this thing loop forever and it will never detect any RAM problems at all on this system with this chip misinstalled. And I can tell you with 100% certainty that I have repaired computers on this channel where I have had page errors that did not come from having the wrong RAM chip installed, but there was actually a problem inside the circuitry in the chip itself that was causing these page errors, like probably one of the inputs was bad or whatever was going wrong. Very difficult to diagnose, and it's not helped by the fact that tests like this and the BIOS's own RAM tests don't show a problem at all. That brings me to Rudd's Diagnostic ROM, which is a modern diagnostic ROM that was created by someone who was fed up with the fact that all these other ROMs sucked for testing stuff and wanted to make something better. Now, I haven't really used this very much, but I have tested it out a little bit just to see if it could detect different types of memory issues on the types of motherboards. And I have a copy of it loaded up into this EEPROM here. And before I even show the results, I do feel that this is probably the only diagnostic ROM that anyone should ever use on a PC XT if you're trying to fix any other types of issues. And that's really because the author of this tried to do their best to make this a better test than this landmark one or the super soft one that we were running. And I'm going to say right off the bat that this diagnostic ROM is way better than the super soft one. And I don't think if you're going to do any testing on your XT that you should even bother using the super soft one like I've done before. You should go right to this Rudd test. Now the problem is that the RAM test is still not that good. It's better than these other ones, certainly better than that, but it's still not great. Now you notice here, it has not detected any kind of problem with the page error, right? Because I have the wrong RAM chip in here. But the author did code this to try to detect those types of problems. And they did that by including various types of RAM tests pulled from different sources. And I think there's a RAM test that was used by IBM in their original BIOS, and then a couple other ones like the RAM test that's used in the, what is it, this one here, the PC Turbo BIOS or the XT Turbo BIOS, the one that I was showing earlier. I think it runs multiple different RAM tests, and it's doing that right now. The thing is, when it gets to the RAM test that does detect this particular issue, and it will in a second, you're going to see that it doesn't give us any kind of useful results whatsoever. While we wait, notice that this is version 5.1 with a release date of July 13th, 2024. So we're talking pretty modern stuff. Good thing about this, I think it's open source, or at least the source code is available, and that means that it can be upgraded with additional RAM testing capabilities, including potentially the RAM testing capabilities that's inside the diagnostic ROM that I'm talking about in this video that David made. That would ultimately make this pretty much the go-to test, because as you can see, this tests other things as well, like the DMA and timers and stuff like that, which the David test doesn't run or test at all. Now I'm noticing here it says top of RAM is 640K. And I think what it does is it scans quickly the memory and tries to find the top of memory. Well, the issue with that is it's possible you have an entire bank of RAM that's missing, and then you have additional RAM. And because it might stop testing or even looking for memory once it reaches a spot where it thinks that it's done looking, then that means it's not going to test all your memory. The test that David wrote tests all the memory, whether it's there or not. So you could have no memory in the first 3 banks, then have 64K all the way at the top of your memory space, and it will test that memory and show whether it's good or not. And I think this test will not do that. And that's sort of a common problem with a lot of tests. They try to figure out how much RAM you have, and they say, oh, you only have 512K, and then they don't test anything else after that. And that's really useful for cards like this, and that snow pattern is pretty cool, isn't it? Where you might have a gap due to a configuration error between this memory and what's on the motherboard, and it might not even tell you that that's a problem here. It will just see, hey, you have 256K, if that's all you have on the motherboard, because that gap tricked it in stopping, and there you go. It's never going to even test this memory. But David's test will test the memory on the card. Well, I happen to know from previous testing, before I started recording this video, that it will detect the page error. It's not what's happened here. I don't know what's happened here. What's happened here is something else. I'm just interjecting while editing. I just noticed that in a previous run, this actually caught the page error where I had that wrong RAM chip in there. But as you notice, it only displayed the memory location the error was happening, which is the same we got with the parity error. Not helpful, and it doesn't show the bit. But for whatever reason, it's actually passing on all the address errors, and we're getting a failure on the slow refresh, which I actually never reached before, because anytime I would run the RUD's diagnostic, it would just halt on the address error. So it's telling us we have a failure at 133 kilobytes. It's telling us that bit 2 is the problem. But when we look at the motherboard, the chip I replaced is that one. This row of chips is 0K to 256K. This is 256K to 512K. The error exists from 256 to 512, not in this bank right here. I think the problem that is detected here is not a real problem. So I don't know what's going on with this. It's coincidental maybe that bit 2 is the one that's saying is bad, which is this chip, which happens to be in the same row as the 64K chip. But I don't know. I'm going to power cycle this and let this run through again. Look, it stopped at the exact same location again. So I guess the only thing to do at this point is take out the 64K chip that it seems to be incorrectly identifying, put back in the original one, run again, and see if indeed maybe we just have a bad RAM chip on the motherboard. It's possible that we have a failure in that bank, and I'll be really curious if it still detects a problem. And look at that. It has stopped in exactly the same spot, 133K. So this chip is bad. Now this is a perfect opportunity to switch back to our test and see if we can detect a problem. Now what's really curious to me is that that particular error only shows up in a much later phase on the RAM test on the RUD's ROM. So it's obviously a very subtle issue that's not being picked up by these bit pattern tests. I'm curious if our test is going to pick this up, and this could actually be a very useful subtle error for us to test against so we can improve the code in this ROM to get to the point where it can detect that we have some bad RAM, subtly bad RAM on this motherboard. So with that, I will go to bed and we'll see where this is in the morning. And I'll do a jump cut. So for you, it'll just be a moment. And for me, it'll be tomorrow. So while the motherboard sits there running our new diagnostic ROM all night to see if it detects the error, I started talking to David about the memory error that RUD's diagnostic was detecting. And he pointed out that there are various RAM tests that are running. They're documented here on this page. But the test that's failing is the slow refresh test. And it says here, do a slow refresh check of the found RAM. This is the same test as the slow refresh test found in the SuperSoft or Landmark diagnostic ROM. Specifically, what it's doing is it sets the timer 1 to a period of 2 milliseconds. That changes the DRAM refresh cycle that's happening on the motherboard. And the setting of 2 milliseconds is very far out of spec. The stock setting that is recommended by the DRAM manufacturers is 50 microseconds. So what it does is after changing the refresh cycle, it fills the RAM with 55, waits 10 seconds, reads back, etc. It does this stuff right here. And it's looking for any cells that decay during this out of spec sequence. And going to the original manual for the SuperSoft test, it says here that this test works by slowing down the refresh rate, writing a pattern to the memory, reading back the RAM after a 10-second delay. Any weak cells in the chips will fail. A chip that fails the slow memory refresh test does not necessarily need to be replaced unless it was also failed in the system memory test. On the other hand, the system is being plagued by intermittent memory errors. The first chips to be replaced should be the chips that fail with a slow memory test. Well, I feel that this particular test is not really a good test. It's running the RAM out of spec. According to the datasheets, and I looked at several different ones, they should be running at 4 millisecond refresh intervals. When you calculate 15 microseconds by the number of rows that are actually refreshed, it is around 3.84 milliseconds. So there's a little bit of leeway to still run it in spec if you actually slow this down a little bit. But 2 milliseconds, we're talking 130 times out of spec. It's way out of spec. So I feel that maybe this is a useful RAM test for finding slightly marginal things, but I don't think this RAM test should result in the diagnostic halting entirely and saying that you have a bad RAM chip. Welcome to the next day. Let's see if the burn-in test running the March test worked and there are no RAM errors, at least on this motherboard. Remember, I'm testing the twin motherboard right now, not the one that had some of the RAM errors before. And there we have it, pass number 182, and we have no errors whatsoever. So that slow RAM refresh test on Rudd's test and presumably the super soft test indicated that this RAM chip right here was bad, but in normal use and operation of the machine, running this test all night, no issues whatsoever. Cool, so I wanted to demonstrate a couple other features that I've talked about a little bit, but I just wanted to show them off. So turning the computer off, there's a jumper over here on this particular clone motherboard. And if I remove this, what it does is it turns the computer into 256K max. It changes these two banks from 256K each down to 64K each. So you have four 64K banks for a total of 256K. Turning the computer back on, it just gives us an idea of what it's going to look like when you have, well, only 256K. Remember I talked about the fact that this ROM always tests all the memory. It doesn't try to figure out what the top of memory is, it just tests it all. The FF indicated on those upper banks is just telling us that, well, all the bits are bad. And of course they're bad because they don't exist. So now this motherboard only has 256K. I'm going to grab my RAM expansion board. This is the one that I have on my GitHub. And the cool thing about this is I can enable banks of RAM anywhere on here that I want. I'm going to enable switch 4 and 5, which is going to add RAM from 384K up to 640K, which will leave us a gap in the memory on this system. So each one of these switches 128K, so that's the first 128K, the second 128K. That memory is already represented here on the motherboard. I'm going to leave a gap here, and then I have these two switches enabled. With this installed in the motherboard, we'll power it on. And now when this runs, you see there we have an FF gap, but now we have working memory, and the little LED is turned on here on the RAM card. It's hard to see in the small view there, but this test is just going to happily go ahead and test all the memory that is currently available and not bad on the motherboard. And I feel this is very useful because for cards like this, where you don't always know the way that these switches work, you might have this misconfigured where you have the memory starting at the wrong address. And if there's a gap and you run a normal memory test with a BIOS or a lot of the other diagnostic ROMs, it will just test and abort when it feels that it's found the top of memory. But with our diagnostic ROM, it will tell you where you have this memory configured, which is pretty useful. Now, when it comes to this bit pattern testing, David reminded me this morning that this testing is not simply just writing a bit pattern into the memory and then reading it back. That's a very simple way of doing it, which is really the way most other RAM tests work. This actually uses a special algorithm to hammer the address lines and read-write very rapidly as it goes through and does all of the testing. Apparently that type of testing is very stressful to the motherboard components and the design of the circuitry, and it can uncover little hidden problems that may only crop up in very, well, specific circumstances when the system is running DOS. So if you have a machine that's sort of slightly unstable, just know that this diagnostic ROM is hammering the RAM subsystem in a way that's really pushing it to its limit. The GitHub repo is going to have more information on the README. Hopefully that's going to be available by the time the video is up to talk more about the mechanics of this stressful testing that it's doing. Now, the final test I want to demonstrate is I want to show what happens on a system that has no RAM at all. And the way to simulate that, if I recall, is to pull out this LS245, this buffer transceiver here. I'm pretty sure that this is the chip that's responsible for connecting all of the DRAM to the rest of the system. Now, the reason why this type of testing is useful is because, well, A, if you have a motherboard that has no DRAM and you want to see if it works, that's a good way to do it. But also, there could be a problem with the way the buffer transceiver connects the DRAM to the rest of the system, or maybe the way that this chip is selected. And that means that the diagnostic ROM is going to be able to show you that the system is running. And if you power up the system and you have all the DRAM installed, but it shows up as all bad, then you know there's probably not a problem with the DRAM itself, and almost certainly the problem was with the logic or the circuitry that connects the DRAM to the rest of the system. Let's see if I guessed correctly by pulling out the right chip. When we turn this on, okay, so the system is there, and there we go. We have no RAM at all. So I guessed right with the chip here that was responsible for connecting the DRAM to the rest of the system. So there you go. It's run through the March test and it's run through the bit pattern test. And the reason why you have so much snow now is because it's speeding through doing all the testing. Just everything is marked as bad, and it's using the stack a lot in the video card, which is creating all that snow. Now, if I install the XT Turbo ROM here, let's see what happens. I'm just curious what it does without any RAM available at all. I assume nothing. Yeah. So it's not even initializing the video card, which is why we just have this static here, which is a side effect of the way I've modified this CGA card. And in case you're curious, let's hook up this postcard speaker to the speaker output on here, just so we can see if we're even getting a beep code on this particular ROM. I heard a click. That's it. We got a single click and no beeps. Now, if I put in the old SuperSoft test here, the diagnostic test, this is going to actually initialize the system. But there we go. We actually are getting beep codes now. And we're actually getting some kind of codes displayed on there as well. But it's telling us that the 16K critical memory error failed. And I'm just going to unplug the speaker now since we don't have to listen to that. As a side note, Rudd's diagnostic ROM would also work on this system with no system memory. And it would just give you an error to say, hey, you have no system memory. So I hope I've sufficiently explained why I think that the diagnostic ROM that David has created is a really useful tool set if you're trying to work on machines like these PC XTs. It just does a really good job of doing burn-in testing, but also finding errors and making sure it reports them in a way that is useful and actionable. Now, what I haven't talked about yet in this video, other than just some little stuff briefly in the intro, is this motherboard that was causing me so much grief with the RAM errors, and then this AST Mega Plus 2 RAM card. Let me plug these in and get these booted up, and I want to demonstrate that, well, everything is just working with these cards right now. And I want to reiterate that the way this motherboard is currently set up with the DRAM that's installed, the CPU, the 8288 as well, and all the other ICs is exactly the way it was when I was having all that trouble with it. And with this jumper removed, it's just sort of off to the side here. This motherboard is configured to actually operate in 256K mode, even though these two banks are 256K each, so this has 640K. But yeah, when you take that jumper off with this clone at least, you get 256. I'm going to put this Mega Plus 2 card in here because this is currently configured to provide an additional 256K starting at the top of 256K. So with this memory plus this memory, this motherboard will have 512K. And I'm going to install this ROM, which was the original one that I did all my testing with when I was trying to figure out what was wrong with this system. And this is just the XT Turbo ROM, which I've already demonstrated a few times in this video. And it's counting up the RAM, and it's doing the very rudimentary test. But before, if you check out those videos on this motherboard, it was always failing just during those RAM tests. We'd get things like error 2, error 3, or then sometimes the system would go to boot and then we would get random parity errors. Sometimes it would happen immediately, sometimes they would happen once it got to DOS, but it actually almost never got to DOS, and it usually had those system error 2 and those weird system errors at the very early phases of the RAM check. But look what's happening right now. Everything is just working. So let's run check it, and I'll do the memory test in here. Now keep in mind, before, when this motherboard and this RAM card were having issues, I could never even get to this point. You couldn't run any software. You would always have the system crashing by this point. So we can go test memory, and you'll see that we have just 512K, and we'll hit enter, and we'll let this run. And there we go. The RAM tests have freaking passed. And while I just did a quick test there, I can assure you that I have let this thing run the comprehensive RAM check, and I've let it run continually overnight, and there were no issues at all. And switching over to our diagnostic ROM here, that RAM test with the March testing also reveals 0 issues. And setting the motherboard to operate in 640K mode and taking this AST RAM card out, it also runs perfectly, and it can run all night with no issues. I can also assure you that I have done absolutely nothing to either the motherboard or this card since I made those videos. In fact, this RAM card, once I was done with that video where it wasn't working, I just stuck it over on the side there. It was actually propped up against my TV back there, and I did nothing to it. And when the motherboard started working, I went and grabbed the AST RAM card, stuck it in the motherboard, and it was magically working as well. So I have been racking my brain as to what has changed down here in the basement that has suddenly allowed both of these things, which were having all these weird random issues, to just start working perfectly. The only thing that I've actually done to change anything is this: the power supply. Now, this power supply is an ATX power supply that I've been using for a while now, and this is a P4 era power supply, and I kind of like it because, as you can see here, we have the minus voltage rails, and it has a very beefy 5-volt rail here at 35 amps because this power supply came from the P4 era. And while it's an ATX power supply, I just use this adapter here that goes from ATX to AT, and it has the power switch on it. I've been using this adapter and this power supply for a while now. In fact, I started using this particular power supply when my AT bench power supply, which I used exactly like this, I would just place it here, I'd put a mouse pad on top of it, and then I'd put the motherboard on it. When that AT power supply died, it actually killed the motherboard that was attached to it at the time. And then I started using this one because it's just one of the various ones that I've saved over the years and started using. Well, a few weeks ago, I was just moving this bench power supply because I often unplug it from whatever I'm working on and put it over on a shelf over there or whatnot. And I heard something kind of floating around inside. And I thought, oh, that's not so good. It didn't sound like a screw. It just sounded like something light, maybe plastic or whatever. So I opened it up to see what was floating around inside. Well, it turned out it was just a little bit of hot glue that was used for some of the capacitors. And that had just come dislodged. It was just floating around inside. So nothing dangerous. But I took that out. And when I was looking at the power supply, I noticed that some of the capacitors were bulging in this thing. 2 of them, actually. And when you think about it, this thing's from the P4 era, and you know what happened in the P4 era? Capacitor plague. And looking at the caps that were in here, even though this thing is pretty beefy, it's not lightweight, it's got big heat sinks in there, and it seems relatively well designed. The caps were all Capson brand, I think, CAPXON, something like that. I've never actually had any problems with this power supply, at least any that I was aware of. And I don't know, I've tested hundreds of motherboards plugged into this thing, and everything has always just worked just perfectly. So I didn't really think too much of it, but I decided to just replace those 2 capacitors that were obviously bulging. In fact, one of them had started leaking a little bit on the top. It actually had vented, so probably just got really hot. Well, I took the 2 out. One was 2200 at 16 volts or something like that, and the other one was 1000 microfarads. And when I tested them, they both tested terribly, like 100 microfarads each and a high ESR of like 2 ohms or something like that. So I just popped in some new capacitors I just had in stock, put this thing back together. I didn't think really much of it. The thing never had any issues running computers, and it still didn't. But then I wanted to make a video about this diagnostic ROM that I had worked on with David back in May. So I took the troublesome motherboard here, the one that had had all the issues, and I made sure to put it back to exactly the way it was when it was having all the problems. So I put the original RAM back on it, and the original 8288, the one I was testing with originally. You know, I wanted to re-demonstrate the issues it was having, especially in conjunction with our diagnostic ROM. Well, when I did that, and I plugged it into the power supply that I put the new caps in, there were no more issues. It just worked. And I just really couldn't understand what was happening here. How could it just be working? And I wasn't even putting 2 and 2 together that it might have been the capacitors that were in here. So then it got me thinking, what about this AST RAM card? I had been testing the AST RAM card with this twin motherboard, the one that never had a single problem, and that was of course plugged into this power supply. Well, now the AST Mega Plus 2 just worked. It freaking worked perfectly, and it worked fine on this motherboard, it worked fine on that motherboard, it just works. So the only conclusion I can draw is that all RAM issues that I was having with this motherboard and this card were due to this power supply. And maybe it just had a bit too much ripple or something like that on some of the rails. I don't know. And unfortunately, I did the recapping of just those 2 caps. I didn't record it on camera, and I didn't measure anything before and after. I didn't really think much of it. In fact, I don't have those caps anymore. I think I tossed them out. So there's no way for me to even put those caps back in here for us to validate for sure if those RAM issues come back. But that is the only thing that has changed in my test setup. And now the fact that both the motherboard works and the RAM card, it kind of tells me it has to have been the power supply. But it absolutely blows my mind how this motherboard was having RAM issues, but its twin, which has a very similar or the exact same design, but some of the chips are different brands and whatnot, never had any issues. I'm also still completely amazed that I tested so many other motherboards on this power supply, including that 286 motherboard I recently worked on where I changed out the SIP sockets for SIM sockets. I did that work before I recapped this. And again, it had no issues whatsoever. And I don't even know how many other motherboards I've used with this same power supply, probably with those bulging caps. And I never even put 2 and 2 together. So I don't really know what else to say other than it had to have been the power supply, it had to have been those caps, and somehow it was affecting just certain things, and maybe it was the brand of the chips that were in use here, or some of the other logic chips for selecting that were running badly because there was too much ripple. I don't know. If you have any thoughts about what might have been happening or have experienced something like this, where simply changing a couple caps in a power supply made things just magically work again, definitely put a comment down below. I've run into issues with power supplies before that generally manifest themselves in systems being highly unstable or not working at all. And I've never had it where it's so marginal that 95% of things work perfectly and then some stuff just slightly misbehaves. And remember, I was using this power supply before I recapped it and this exact motherboard with no issues. And really it all just sort of started happening when I removed the 8288 chip. That was this one right here to fix that Book8088. And then when I went back to use this motherboard, then it was misbehaving. So that was obviously just coincidental and a red herring. I thought that was the problem when obviously that was not the problem. It was just this power supply was slowly failing little by little. So I suppose moral of the story, when you're having some weird issues like that and you're not 100% sure that your power supply is not the culprit, maybe try a different power supply, and I could have because I have other ATX power supplies, or at least use an oscilloscope to check for excessive ripple on the voltage rails. Yep, that's just something I'm gonna have to think of in the future because it's just not something I've ever run into. And I spent a lot of time trying to fix these particular systems. And hey, we even made this diagnostic ROM for the issues I was having with this motherboard and this card. And in the end, it wasn't even either of them. It was this freaking power supply. So I think I'm gonna end this video here. I have lots of links down below in the description talking about the diagnostic ROM and all the other videos and stuff I've referred to. If you like this video, I'd appreciate a thumbs up. But if you didn't, you know what to do. Hit subscribe. Huge thanks to my patrons. Their names are going up this side of the screen here, and to make it possible I do this full time. And I think that's gonna be that. So stay healthy, stay safe, and I'll see you next time. Bye.